In this video, we are going to continue to talk about atoms, but more specifically isotopes. So, understand that first we are going to be discussing what information can we extract from the periodic table in terms of the subatomic particles that we learned about previously. The periodic table is very informative. In most periodic tables, will give you the following pieces of information, and I'm just going to highlight them to make them easier. They will give you the atomic number, which is going to be the number that is on top of the symbol, which I just highlighted here. Okay. Below the symbol, we're going to have the atomic mass, which I highlighted in green. Understand that the atomic mass sometimes is known as the mass number. So when you hear those terms, don't get them confused. Atomic mass, mass number is going to be the same thing. Now, depending on the periodic table that you're utilizing, it may give more significant figures or decimal places. But understand that the one that I illustrated here gives you two. The one that I posted on the course Canvas site has more decimal places. Now, let's go and specifically understand which subatomic particles or the information for the subatomic particles, where can I find it in the boxes of the periodic table? Now, as you can see here, for atomic number, that is going to equal the number of protons. Now, in this chapter, we're only talking about ground state elements, so understand that the atomic number is also going to equal the number of electrons. And as it has been established by the asterisk, is because we're talking about ground state elements, okay? Now, when it comes to the atomic mass, understand that the atomic mass is going to give us a value of protons and neutrons, but understand that in order to actually do that, we're going to round it to a whole number, okay? That's only when we are doing calculations. So what does this mean? That if you at some point need to find the neutrons for a particular element, you're going to take the atomic mass number and you will subtract it from the atomic number. Now, understand, this is my symbol for number. Understand, and I'm just going to write it here as a note, that the atomic mass number, when you're calculating neutrons, you need to round to a whole number, okay, in order to do this calculation. The next concept that we are going to explore before we talk about isotopes is going to be isotopic notation, okay? Because we need to practice on what are the different symbols and notations that we utilize in this course. So understand that isotopic notation is given to you in the following fashion, in which you have on the top left corner the atomic mass for the element, again rounded to a whole number. Then we're going to have the symbol for the element. And in the bottom left corner, we're going to have the atomic mass, the atomic number. So top left corner, atomic mass, bottom left corner, atomic number, and in the middle we have the symbol, okay? So as you can see, and I just explained in the previous slide, If you're given the isotopic notation, you can easily determine what is the number of protons, neutrons, and electrons. So in order to discuss this, I'm going to specifically deal with the first example that we have here, which is oxygen, okay? So O is oxygen, okay? Okay? In oxygen, as I did in the outline, has a mass, an atomic mass of 16, because when I take 15.9994 and I round it to a whole number, it's going to be 16. So this is the atomic mass. Bottom left corner, this is going to be the atomic number. And when it comes to this, remember, number of protons and number of electrons are going to be the same. I'm just going to highlight them. So the atomic number is going to tell me how many protons and how many electrons I have. And as you can see, 8. That matches that number. Okay. Now the number of neutrons, which is in the middle, comes from atomic mass minus atomic number. That's why if we do 16 minus 8, that equals 8. And that's where that number comes from. So we took this value and we just subtracted them from each other. In order to get the number of neutrons. Make sure that you practice when it comes to this. So, as you can see here in problem 1 of the worksheet, we have an exercise in which you're going to have the element name, atomic number, atomic mass, protons, neutrons, electrons, and even the isotopic notation. So let's take, for example, element 23. Okay, this is vanadium. Okay, atomic number, I already established that it is 23. Atomic mass for vanadium, let's say if I utilize the periodic table that I have on Canvas, it is going to be 50.9415. The units for this is going to be AMU. Okay. Now, when it comes to the protons, again, is going to equal the atomic number. So there's going to be 23 protons and there will be 23 electrons because I'm talking about ground state vanadium. When it comes to the neutrons, they're going to come from atomic mass. So I'm going to round to a whole number, which is going to be 51. I'm going to subtract that from 23. Okay. And when I do this, 51 minus 23 is going to be 28. Okay. So vanadium specifically has 28 neutrons. And again, that 51, I just want to highlight it. This 51 comes from rounding this number to a whole number. Okay? Next, if we have to write the isotopic notation for vanadium, understand that we're going to put the symbol for vanadium, which is a capital V. Then in the top left corner, we're going to put its atomic mass as a whole number. So this is 51. And in the bottom left corner, we're going to put its atomic number, 23. And that's how we do the isotopic notation for an element. Make sure that you practice. Now let's talk more in detail about isotopes, okay? So when it comes to isotopes, these are going to be atoms of the same elements, but they have different atomic mass, meaning different mass number. So the reality of isotopes is that they come from the idea that if a sample is taken from nature, earth, something around us, and we are looking for a particular element, we're going to see how we have different versions of magnesium. So, to utilize an analogy, this is kind of like when you go to the supermarket and then all of a sudden you're trying to get vanilla ice cream. And we have different flavors of vanilla. We have vanilla bean, we have French vanilla, we have homemade vanilla, we have Mexican vanilla. Everything is vanilla, it's just that it is a different flavor. When it comes to the application in terms of the atoms, as you can see, everything is magnesium. It's just that the difference between all these magnesiums is at the level of the number of neutrons. Why? Because each one of these isotopes, and this is just the example that we have in table 4.7 in the textbook for magnesium, the difference between all those isotopes is the number of neutrons. That's why the mass of each isotope is affected and it is different. Okay. Whenever we're talking about an isotope, we always talk about them in terms of the element name followed by the mass. So we have magnesium 24, magnesium 25, and magnesium 26 in this slide. The other point of difference between them is going to be the percent abundance. And the percent abundance basically represents how common an isotope can be found in a sample. So for example, if we compare the three different isotopes of magnesium, the one that is most commonly found is going to be magnesium 24 because it has the highest percent abundance. Why is all of this important? Because when we look at the periodic table and the mass number that is given for each of them, remember the atomic mass or mass number, that number, it is actually calculated taking into account all the isotopes that we have for a particular element. So with that, we are now going to understand how to calculate the weighted average mass method for calculating the atomic mass for a particular element. And as you can see here, when it comes to this comes from experimental data. So somebody in a laboratory is obtaining all of this. Let's look at how this method works. You're going to be given the isotopes for a particular element. In this example, we have chlorine, specifically chlorine 35 and chlorine 37. Okay. In addition, you will be given the mass of each isotope, and as you can see, that's the second column. Chlorine 35 has a mass of 34.97. Chlorine 37 has a mass of 36.97. Then you're going to have the percent abundance for each isotope. As you can see, out of the two isotopes, chlorine 35 is the one that is most commonly found because the percent abundant is 75.76. So in the method for calculating the atomic mass for a particular element, given experimental data, as you can see, you're going to take the mass number, you're going to multiply it by the decimal conversion of the percent abundance. So the percent abundance, you're just going to divide by 100 to find that value in decimal place. And then you're going to obtain the result. You're going to do the same calculation for every isotope that you have. In this one, we only have two. Then, as a last step, you're going to add, okay, each of the contributions that each isotope has, and then that's what is going to give you the final answer for the weighted average mass for a particular element. So understand that this final value is going to be very close to what you find in the periodic table for a particular element. So as you can see, in our worksheet, we have the following problem. You're going to be utilizing the following experimental data, and the weighted average mass method to determine the average atomic mass for the following elements. So there's two problems on the worksheet, but this one specifically is the one for lithium. So let's go through this problem. As I mentioned previously, the way that you do this problem is by taking specifically, okay, into account the information given. So we have lithium 6, and we have the mass of that isotope, which is 6.015 AMU. We have lithium 7, which has a mass of 7.016 AMU. Then we're going to convert the percent abundance, so 7.50, we're going to divide it by 100. You can put the percent signs if you choose to. We're going to take 92.5% divided by 100%, okay? So we're going to do each one of these calculations. So the contribution of lithium 6 is going to be 0.451125 AMU. The contribution of lithium 7 is going to be 6.4898 AMU. When I add these two values, then the final answer is 6.9409 AMU for lithium. Understand that this value is very close to the one reported at the periodic table. Understand that whenever we're doing these problems, significant figures is something that you can take into consideration. But when it comes to actually performing these problems in an exam, I tell you what the final answer need to be rounded to. So I may say, hey, round it to 4 sig figs or round it to 3 decimal places. So just make sure that you read the instructions for writing the final answer in this problem.